Welcome to EE252 Electronic Devices and Circuits. Today we are going to talk about analysis of BJT circuits using H-parameter model. Now, in the previous lecture we looked at how to obtain H-parameters for a particular BJT using input and output characteristics. Now today we are going to use those values, H-parameters, to analyze a BJT circuit. Okay. To begin with, we are not actually going with an actual circuit, but we are going to represent everything as a load and a source, voltage source and a load, which is like basically the Thevenin's equivalent circuit of the external circuit, right? So this is basically what we are going to do, and also we are going to assume certain things for this particular case. This is, we are only looking at the steady state where inputs are where the circuit is properly biased, BJT is properly biased, and the input is a sinusoidal signal which is at steady state. So because of that, we are not going to look at the transients. We are only looking at the steady state values. So therefore, we can, instead of using AC and DC quantities, we can use as phasor values. Okay, so RMS currents and RMS voltages. So that's one thing that we are going to do. And another thing that we are going to do is we are not going to take any particular configuration, like for example common emitter. We are going to use generic or the common terminal common H parameter values HI, HR, HF and HO without the second subscript, that is, so that this analysis can be applied to any configuration, common emitter, common base or common collector. Okay, so that's what we are going to do. So let me start with that. Okay, so let's look at the circuit. We are going to replace our BJT with its small signal model, the H parameter model. So what we have is simply the HRE times V2, so V out, the HFE times the input current, the HO. This is my BJT. I'm not going to mark base collector emitter because that can be anything. And that's my BJT. The external circuit I'm going to represent as a Thevenin's equivalent circuit. Output, let me assume it's just a load, so that it's, let me mark it as a general impedance rather than a resistance, ZL, load, and the input replaced with its Thevenin's equivalent, but I'm going to replace it as a source. So these are actually the Thevenin's equivalent circuit of the input circuit. So this is my Vs. Let me use phasor notation. So this is V, capital V, simple S. Right. So this is my input, source resistance, and I have the first port, 2-port device. So I have 1 and 2, and let me mark these as I1 dash and 2 dash, the negative terminals, and let me mark the load current as IL, whereas my convention for the output current was in this direction, that was my I2. Okay, so then I had HI. Mind that I am not using any second subscript, so this can be used for anything, any configuration. So this is HR times V2, that is, this is V2, this is V2. I'm using phasor notation, so it is capital, and this is I1 input current. This current is HF times I1, this current over here, this current times HF, and my output conductance is HO. So therefore my resistance is 1 over HO. Okay, if I'm marking as a resistor. So these are my values, and this is basically what I'm going to look at. This is my circuit. This is my input voltage V1. So this is capital, right? So I have all my things. Now mind that sometimes we can represent my input as a Thevenin's equivalent circuit or a Norton's equivalent circuit. Either way, this is a source. I'm going to represent it as a source. Now what are the things that I need to find? I need to find out what is my current gain for the entire circuit, what is my voltage gain, current gain, voltage gain, what is my input impedance, and my output impedance, or more generally, more suitably, output conductance 1 over R out. Okay, so those are the 4 things that we are going to look at. Okay, so how are we going to find all these things? So let me mark the input impedance looking into this, output impedance looking from here. So these are the terminals that I am interested about: Z out, Z in. Okay, so sometimes I can also replace this with the Norton's equivalent circuit, in which case what I have is something like this: IS, this is my RS, and Z in would be something like this. Okay, as what the source sees as a load. Okay, so this is basically what we have. How are we going to do this? First one is the current gain. Let me first see what is the current gain, AI. Now let's first define what is this. AI is defined as, so this is a definition, that's why I put this small triangle, is equal to the load current divided by the input current, IL over I1. Now if you look at this circuit, you see that load current is flowing out of the circuit, whereas my conventional output current I2 is flowing in. So therefore this can also be written as minus I2 divided by I1. This is my definition. Okay, to find this, what I'm going to do, I need a relationship between I1 and I2 alone in terms of all these other parameters, circuit parameters. Okay, so what I'm going to do is I'm going to apply this Kirchhoff's current law to this terminal number 2. Okay, if I apply the Kirchhoff's current law, KCL to 2, we have I2, this is the current that is entering, I2 is equal to this current, which is that HF times I1, plus this current, which is equal to voltage divided by the resistance. Voltage is V2, resistance is 1 over H out, HO. So therefore current is V2 times H out. Okay, so therefore I can write this is equal to HF I1 plus V2 H out. I'm sorry, HO. Okay, but also we know that V2 should also be the voltage across the load. So therefore I2, which is the IL times the load resistance or load impedance in general. This can be resistive or non-resistive. It could be an impedance in general. So what do I have from that? I2 then is equal to HF times I1 plus, instead of V2 I'm going to use the previous expression that we derived, so therefore it is minus I2 ZL times H out. So from this is I2, so now I only have values in this expression. I only have I1, I2 and the parameters of the circuit element. So therefore I can write an expression for I2 divided by I1. I2 you have here, and then you have I2 here also. If I take this I2 to the other side, I get I2 1 plus ZL times HO. So therefore, and the right hand side I have HF I1, so I end up with the expression 1 plus ZL H out. Okay, that is my expression for AI. So AI is this. So I know my current gain in terms of the circuit parameters. Now mind that the ZL, the load impedance, is also there. Obviously, current depends on that. So it's the current gain of this circuit depends on the output load, that the load that is connected to the circuit. Now the next thing that we are going to find out is the input impedance Z in. Let me define what that is. Let me call it ZI. ZI is defined as the definition: input voltage divided by input current, that is I1. So V1 divided by I1. That's the definition. Okay, but if I apply the Kirchhoff's voltage law to the input side, V1, this is equal to this plus that. This is I1 times H1. This is HR times V2. So therefore V1 is equal to HI I1 plus HR V2. So what we need is an expression between V1 and I1 alone. But in this expression we have V2. We need to eliminate this V2. How are we going to eliminate V2? We write an expression of V2 in terms of others. Okay, but we already have seen that V2 was equal to minus I2 times ZL, that we already saw. And also we saw that I2 was equal to minus AI times I1. Why? This is the definition of current gain AI, and we know an expression of AI in terms of other terms. So therefore I can say V2 therefore is equal to minus minus plus. I have AI I1 times ZL. This is my V2. Now I can represent this as HI I1 plus HR times V2, which we find as AI I1 ZL. Okay, so therefore now I have an expression for V1 divided by I1, that is equal to HI plus HR AI times Z load. That's my expression for Z in, right? It's my input impedance Z in. I can actually expand this AI in terms of circuit parameters. So ZI is equal to HI plus HR ZL times AI, which is HF 1 over 1 plus ZLH out. Okay, that's my expression. This can be further simplified as HI plus, if I divide top and bottom or the numerator and denominator of this second term by ZL, I have HRHF divided by 1 over ZL plus HO. And noting that this term 1 over ZL can be written as, this is the load admittance. Okay, this is load admittance. So therefore I can also write this as my input impedance is equal to HI plus HR HF over YL plus HO. HO is an admittance, and we are representing the load as also an admittance. This is my output impedance, sorry, input impedance, my second quantity that I am interested about. Note here again that my input impedance depends on YL. In other words, 1 over ZL, that is, it depends on the load. So if I don't have a load, that is, if it is open circuit, my input impedance will be one thing. If I have a load, input impedance will be different. So therefore, this is an important note. Okay, so let me write it here. Note that the input impedance depends on the load. Okay, so that is important, right? So we have now 2 quantities out of 4. The next thing that we are going to look at is voltage gain. The voltage gain AV is defined as V2 over V1, output voltage divided by input voltage. We already have an expression for V2, okay, which is AI times I1 times ZL, that is V2, divided by V1. But we know if I divide both by I1, what I have here is ZI. Okay, so therefore what I have in this is AI ZL over Z in. So if I want to, I can express AI and ZI in terms of the circuit parameters, but I'm going to leave it as this is. So you can mark this as AB. Okay, now before we actually go into output conductance, one important thing that we need to focus on is my source. Now I had a source represented by a Thevenin's equivalent circuit which had a output resistance RS. Now what is the effect of this in my circuit? Now if I want my voltage gain to be the voltage ratio of voltages at the load divided by the voltage generated by the source. Okay, so if I define it as such, okay, voltage gain when source resistance is included, let me call it AVS. Let me define AVS as its definition V2 over Vs. Now I can write this as V2 over V1 times V1 over Vs. We know V2 over V1, which is AV, right? So AV times V1 over Vs. We don't know what V1 over Vs is. We need to find. But if you look at this circuit, it is clear that V1 over Vs, this is V1, this is Vs. What you have is I can replace this whole circuit with Zi, input impedance. So therefore I have voltage or potential divider. Input voltage is Vs. I have two impedances. One is the Rs, output of the source resistance, and the other one is Zi. So it's easy to find the output the voltage V1. So the V1 is equal to Vs times Zi divided by Rs plus Zi. Okay, so voltage division. So therefore it is easy to find AVS by replacing V1 over Vs. So V1 over Vs is Zi Rs plus Zi. So therefore my AVS is equal to AV Zi over Rs plus Zi. Okay, from the voltage gain equation I can represent this also as, okay, AV Zi over from this equation, AV Zi term is equal to AI ZL, right? So therefore AVZI term you have in the numerator here, so I can represent it as AIZL divided by VRS plus ZI. Okay, so both are okay. So this is my voltage gain with the effect of the source resistance. Again, note that if RS is approximately equal to input impedance ZI, then AVS is actually equal to 0.5 times AV. See, from this expression, ZI divided by this expression. So if RS is equal to ZI, then you have what you have here is 0.5, half. So if you have a large output impedance for a voltage source which is in the same order as the input impedance, then half of that voltage is half of uh, the voltage gain is going to be lost. Okay, you are only going to have half the voltage gain. In other words, half the voltage is dropped across my RS. This is the reason why it drops. The second one that we need to note is our overall voltage gain AVS is appreciably affected by RS, output resistance of the source. So those we need to remember. The next thing that now if the voltage gain is going to get affected by this, why not we find what's going to happen to the current gain when the source resistance is included. Okay, current gain when source resistance is included. Okay, let me define it as AIS, defined as minus I2 over IS, where IS now we are going to represent my source as a Norton's equivalent circuit, not a Thevenin's equivalent, in which case I have my input would look something like this, not instead of this. Okay, instead of this I'll have IS and RS. Okay, so if this is the case, my AIS is equal to minus I2 over IS, which I can write as I minus I2 over I1 times I1 over IS. We already know the first term, which is AI times I1 over IS. What is the ratio of I1 to IS? So obviously from this circuit again, if you consider this as my Z in, my current through my this terminal I1, this is IS, so this is the IRS, the current that passes through that. We know the current ratio. This I1 will be equal to RS times RS plus ZI times IS. Okay, similar to potential divider, this is a current divider. Right, so I can write this as AI RS over RS plus ZI. That's my AIS. Next parameter that I am interested about is the output impedance, but let's find the output admittance instead. So it is the one more. Why we are going to do that? Because output is represented as a current source or the Norton's equivalent circuit, not a voltage source. Okay, so I'm going to find YO, okay, output admittance, which is equal to 1 over output impedance R out. Okay, that's what we are going to find, or Z out, 1 over Z out. Okay, so let me define it. Y out is defined as I2 divided by V2, but under special circumstances, with the source short circuited and no load, RL equals to infinity. So under these conditions, this is my definition. So this is how I define what my output impedance is. When there is nothing connected, to the output, but the voltage input is 0. Okay, but the input resistance may be there. Okay, so we can write this as y out is equal to I2, which we already found in previous occasion. So therefore that is equal to HF times I1 plus H out V2 divided by V2. So this is equal to HF times I1 over V2 plus H out. Now what we need is to find what this I1 over V2 term is. Now to do that, let me apply Kirchhoff's voltage law to input side, which gives me, so input side, which gives me Rs times I1. So let me go back to the circuit so that we can first look at it. So I have Vs equals this plus this plus this. Okay, HR plus HR times V2, I1 times H1 plus I1 times Rs. So I can write Rs times I1 plus Hi times I1 plus HR times V2 is equal to Vs. Now we said in the definition that Vs should be equal to 0. So therefore this should be equal to 0 by definition. Okay. So therefore we only have I1s and V2s in addition to the parameters of the circuit. So you have I1 over V2 is equal to minus HR over Hi plus Rs. Okay, so this gives me my output impedance Y out as Y out is equal to H out minus HF times this term HF times I1 HF times I1 over H out minus, because this term is minus, so that is why HF times HR over HI plus Rs. That's my output impedance, which is also equal to 1 over output impedance. That's my last term. Okay, so this is basically what we need to find. So let me summarize everything in these terms. Here's the summary of all the expressions that we obtained, but remember, you do not have to remember any of these because it depends on your circuit, and you will never have to remember any of these circuits. Don't memorize any of these. These are just there for your information. You will have to derive your own expressions if you have to do it in an exam. So therefore, don't spend your precious memory cells to remember these things. Okay. All right. So today we'll stop at this point.